The guest of honor of today's event has arrived, so I request everyone to welcome them by giving a big round of applause. I request all the dignitaries to have their seats. First of all, a very glorious and good afternoon to one and all. Today we all have gathered here for a seminar on the three body problem and its application, the earth, the moon and the sun, by Dr. Najm Hasan sir. Sir, every Thursday we eagerly wait for eminent personalities like you to have a healthy interaction. Today I would like to convey a message to you on behalf of all the students of Hyderabad Institute of Excellence that we are super excited for your service session. The three body problem refers to the long-standing physics problem of predicting the motion of three celestial bodies. While this is well understood for two bodies like the earth and the sun, it's turned out that adding a third body makes the problem much more complex. Now, I would like to call Master Mohit to welcome the gathering.
Science and technology were only keys to opening the door to the future. Leo's vision, the three-body problem. A very warm and graceful good afternoon to everyone. It gives me an immense pleasure to start this auspicious occasion by welcoming everybody. I heartily welcome our guest of honor, Sir Najm Hasan sir, committee members, director sir, principal ma'am, teachers, and my fellow students. Today, we have gathered here for our 20th episode of Thursday Table. a series of webinars and seminars to interact with eminent personalities, a seminar on the three-body problem and its application, the sun, the earth, and the moon, by Dr. Najm Hasan sir. It gives me great pleasure to introduce our today's guest of honor, Dr. Najm Hasan. Professor S.N. Hasan is presently at the Department of Mathematics in Maulana Azad National Urdu University. He has been head of Department of Mathematics, Dean, School of Sciences, Maulana Azad National Urdu University. Before joining MANUU, he was head Department of Astrology, Astronomy, Usmania University in Hyderabad, and Director Japal Rangapur Observatories. He completed his MSc and MPhil at University of Hyderabad and PhD at the Moscow State University in Russia. He was recipient of National Merit Scholarship, University Merit Scholarship for his master's program, and Ministry of Human Resource and Development, Government of India Scholarship for doctoral studies. His research interests are celestial mechanics, dynamical astronomy. He has published his research in national and international journals and has more than 25 years in teaching. He has traveled and delivered lectures in Russia, New Zealand, Europe, and Egypt. He is actively involved in Olympiads, public outreach, and science popularizing program for children and adults. Thank you.
Thank you very much, Mukhit, for welcoming the gatherings and introducing our chief guest. Now, I would like to call Dr. Najm Hasan sir to address us.
Hello, good afternoon. Is it evening already? Yeah, good evening, just four. And I would like to thank the organizers for having invited me here, and the principal ma'am, Mrs. Prabhavati ma'am, for giving me this opportunity. It's always a pleasure to speak to young, bright minds, and because this is the age when you are most receptive, and it's good talking to you. And I hope that I don't bore you, because there are some in the audience who feel mathematics is a boring subject. I believe, contrary to that, it's one of the most beautiful subjects, and we'll see what all mathematics can do. So, shall we get to the program? Yeah. And I'm very happy that in the introduction itself, one of your friends said what three-body problem is. He did some homework, and he is absolutely correct with what he said. The three-body problem yeah. Yeah, so if you have two bodies, three-body problem is if you have three celestial bodies, like your friend said, like the Earth, Moon, and Sun system. Can we predict their motion? Can we? And like he rightfully said, that if you have two bodies, if you just have Sun and Earth, it's very easy to write the equations of motion and solve them. But when the third one appears, it becomes very complicated. And we look at this three-body problem. And the reason why I chose this topic is, one, it's very dear to me. I worked in this for over 25 years in different aspects of it. And it's a problem which has baffled mathematicians for over 400 years. So it has been at the center stage of celestial mechanics for over 400 years, and the best minds, right from Newton to the 20th century Kolmogorov, you name Lagrange, Lyapunov, Poincare. I think this is fine. You can hear me, right? It's okay. You can hear me? Yeah. So, I'm sorry, that's probably getting annoying where you have the three bodies, the sun, earth revolving around it, and the moon moving around it. And this is the genesis of the three body problem. And it is that problem which even Newton, a person like Newton said, it gives him headaches. Right? So if you have heard of L'Hopital and Lagrange and Hamilton and Poincaré and the best mathematicians have contributed tremendously, have taken an attempt at this problem, and this has led to development of a lot of mathematics, right from something called calculus. Do you learn calculus in school? Differentiation and integration? Yes. Oh, no. Yes, yeah. So calculus was formulated by Newton trying to solve this problem. And then an area of mathematics called perturbation theory, it came up because of this. An area which is called topology, that was also developed trying to solve this problem. And in the 20th century, this led to a very beautiful theory called calm theory, Kolmogorov-Arnold-Moser theory, which tries to deal and look into chaos and see patterns in chaos. Chaos is disorder, right? So mathematics touches upon almost everything, and we'll have a look at that. All that I think I've said before without having to see. So the three-body problem is the study of motion of three mass points moving under the mutual gravitational attraction. And you just see here, even if you treat these Earth, Sun and Moon as point objects, it is a complicated problem. And if you treat them as extended bodies, right, take them as spheres, it becomes slightly more difficult. And if you take them as ellipsoids, like for example, Earth's polar diameter is slightly less than the equatorial one, which makes it an oblate one, a squeezed sphere. It makes the whole thing even more complicated, right? So hence Newton said that it gives him headaches, this three-body problem. And yeah, so and it has a lot of relevance to a lot of things which we do, because most of the planetary theories, lunar theories, are based on this understanding of the three-body problem, and even the artificial satellites which we have in our orbits, which help us communicate with each other through our cell phones, and you book an Uber and you get Swiggy food delivered to you, is because these satellites are moving around and they are there in stable or almost stable orbits, because we have understood this three-body problem to some extent, so that we can make it work for us, right? So this lies at the essence of many things. So before I continue with what the three-body problem is, what is mathematics? What does it deal with, and why do we need to study mathematics, right? So just a slide or so on that. Yeah, so the first answer when we say what is mathematics, people say it deals with numbers, right? Which is right. It does deal with numbers. And you have a host of numbers. You have the natural numbers, you have integers, you have complex numbers, and so on. And these become very essential for various areas of human endeavor, right? Without numbers, you cannot imagine life. There's no economics without that. There is no reaching in time for your class without a number. And so it's taking mathematics by the simpler side. And you also can replace numbers by some variables, like x plus 2 is 7, what should x be? And it's a trivial thing, x is 5, then it's solved. But then when you have things like x square equal to minus 1, right, like x square plus 1 equal to 0, which says x square is minus 1, what is that number which multiplied by itself gives you minus 1? And there is no natural number which does that. So you create an imaginary number. You say there is a number called I, which is an imaginary number, and square of I is -1. And though it is just an artificial creation to solve equations of this kind, x squared by +1 equal to 0, but it becomes very essential when you have to study an atom and you want to study quantum mechanics, right? So we live in a strange world. We have very large structures. The whole universe is extraordinary big. We have galaxies which are 100,000 light years across, and there are thousands and trillions of galaxies which make the whole universe. And on the other extreme, we have an atom, and you have proton, neutrons, and the world were very small. And fortunately, humans are lying somewhere in the middle. And to understand the quantum level, you have to go to these complex numbers, these imaginary numbers. Otherwise, you cannot do quantum mechanics. Yeah. So today we'll not be talking about that, but you take it from me that it becomes essential to deal such problems when you have these things. Right. So second aspect of mathematics is shapes. Yeah, circles, spheres, cones. That's what we study in schools. And so mathematics deals with shapes, lines, circles, and what happens when two planes intersect, and what happens when two lines intersect, and then there are a lot of applications which try to which can be used to understand how markets work, how things work. Right? You are looking at different dimensional spaces, and all these things, they become very meaningful. So on the one hand, you have very concrete, very abstract mathematical objects, but on the other hand, you have these implications and reflections in a lot of different areas of human endeavor. Right. The third aspect, there are many such, but I have just touched upon three so that we can get on with what I basically want to talk about. Third aspect of mathematics, you try to see patterns. Yeah, when you see something, you try to recognize whether there's something common which is in everything, and you try to filter out the essence of it, and you try to see patterns in it. And that's the most important thing of mathematics, and very important, one of the most important things of science as such, right? For example, we see the sun rise every day in the east and sets in the west. And if you notice very carefully, the rising of the sun is not exactly at the same point each day. It keeps shifting, right? It shifts from exact east towards the northeast, and then it goes back towards the southeast, and there is a small oscillation in the rising and setting of sun day to day. So if you every day you try to notice, you will see that small differences. And on March 21st or 22nd and September 21st or 22nd, it exactly rises in the exact east and exactly in the west. And then to calculate this rising and setting, and to calculate the time it has been over the head, you needed mathematics. Right? So mathematics is there almost everywhere. So these patterns are pretty important. So in fact, mathematics is there in our very primitive brain, where the concept of space and time, it is ingrained in our brain, and in fact in all animals. And even the simplest of animals, they have this understanding of mathematics. They have a sense of counting. Though the birds can count up to 3, not more than that. Humans have gone much beyond. And for various reasons, we have learned how to write it down, how to record it, and writing has played a very important role for us to develop all these skills. But if you see that snake coming and eating eggs from a nest, and if the bird knows that there were 3 eggs there and one is missing, they know that there is some danger and they abandon it. So they have that sense of counting. So it's there with our survival. The moment where the leopard has to pounce to catch the deer, and at what stage the gazelle has to escape to save itself. There's mathematics in that, right? So mathematics is there. Time, you have the calendar, you have primitive people counting sheep. They were counting sheep when they would take a few set of sheep out and then came back. They would count whether they have got back all, right? So this has been there in almost everything. When you make bridges like you have on Durgam Cheru, you have to calculate the stress, strain, and there's mathematics in that. What kind of a curvature you have to give, what are the load-bearing walls, and so on. We have engineers sitting here, and you can talk to them that there is mathematics in everything. And all the way to say cyber security. When we send our messages on WhatsApp, we don't want others to intercept and read what you are saying. So all these are encrypted into mathematics. And in cyber security, when it comes to cryptography, the numbers play a big role. There's this number theory. So numbers go beyond from counting things. Most people say, what is there? There was a time when I was doing my PhD in mathematics, and somebody in the bus asked me, what do you do? I said, I'm doing my PhD in maths. And he said, oh, so what do? You multiply big numbers and subtract big numbers? So I said, I'm sorry, but the only numbers which I deal with are the page numbers in my book. So there are certain branches of mathematics where there are no numbers at all. It is only to do with concepts and patterns and so on. So there's a misconception where mathematics people think is just adding, subtracting, and what can be there in mathematics, right? But mathematics is there in everything, right from launching a rocket to understanding how nature works, and it is something very essential for our basic survival. So coming to these patterns, some of the patterns which taught us a lot was looking at the stars rise and set. And it took many years for people to understand that sun was at the center and the other planets were going around it. For a long time, people thought that Earth was the center of the universe. We had mathematics of Ptolemy and physics of Aristotle, which believed in the geocentric system. And then came Copernicus, and followed by Galileo and Tycho Brahe and so on, who have contributed in different ways. And we realized that it was not the sun at the center of our solar system, but rather it's not the Earth at the center of the solar system, but the sun. And they are all going around in certain orbits. And it was the mathematician Kepler. And in these patterns, people saw certain irregularities. They saw that the stars move in a very systematic way across the sky, all of them rising in the east and setting in the west. But they also noticed that every day the stars rose 4 minutes earlier, right? So if a star rises today at 8 p.m., tomorrow it will rise at 7:56 and so on. So there's a 4-minute delay. And to understand why this was happening, they had to use a lot of calculations, a lot of trigonometry and other things to measure their positions accurately and try to understand how far they are from us and what's happening. And the irregular objects which were moving across the sky were the wanderers, the planets, which we today understand as the planets. And we could perceive that their motion was not as regular as that of the stars, was because they were much closer to us and they were rotating around the sun, and we too were changing our position with the sun, right? So we have all these great giants. This is Tycho Brahe, Newton, Galileo, and Kepler. And Tycho Brahe was a brilliant astronomer. He was a very rich nobleman, but he was very fascinated with astronomy, so he set up a big observatory in his house, and he made very meticulous observations of motion of these stars and planets and how they vary day to day in seconds of arc over the days and over the years. And he had a lot of data. There were a lot of numbers there, but he couldn't understand what to do with it. So he called the mathematician Kepler, and though he called Kepler to his house, to his court, but he was scared that Kepler will get the whole credit, so he never gave him all the data. He kept hiding it from him till a time when one day Tycho Brahe died. He believed in a lot of parties and overeating and so on. So in one of those, he died of excess of eating and wine. And when the other people were trying to amass as much of money and things which were around, wealth around, Kepler took his data and he spent 17 years to give these Keplerian laws, the three laws of Kepler. He said the planets go around the sun not in circles but elliptical orbits. They sweep equal areas in equal intervals of time, and the square of the period is proportional to the cube of the distance to them, right? So let's not get into that. But he gave these Keplerian orbits, and it took him 17 years to get these three laws. And and he lived in very acute times. As you were driving down today, we were discussing. That was the time when Europe was going through a very bad period. So he lived through a very bad period. His mother was taken away as a heretic because anybody who had books in the house were considered as heretics. His wife was highly disturbed because some of the children had died. But in all those adverse conditions, he worked consistently, and he revolutionized the whole understanding of our solar system. So many a times we say things are not good, things are bad, we are born at the wrong time. It's nothing like that. It's always a time for you to put your mind and heart to something and achieve, right? So all those who have achieved, they have also gone through miserable times, but they had the tenacity, the dedication, that sincerity to what they were doing, which kept pulling them on and so on. And it is the same case with Newton. So, though he did not specify why they go around this way, so there was a time when it was established that these planets go around the sun, all that was clear. But there was one question which troubled people, and the question was, is this solar system stable, right? We know today that we have sun and these 8 planets, and many of these planets have their own moons. So it's a many body system, and the question is, will someday we spin and get closer to the sun, or will we wander off? Either way, it's going to be end of life on earth. If we spiral into the sun, it will get hotter and hotter, and it will not be conducive for life. And same way, if we spiral out, it would become cold, and it is again death of living organisms, humans on earth. So the quest, or there can be other possibilities, that a meteor comes and falls on earth, or we collide with Mars or moon and so on. So this was a big question, and this debate went on for many years. So is the solar system stable? Oh, so this got messed up. And this is the genesis of the n-body problem, where it says if you study the motion of n mass points under the mutual gravitation attraction, then it's called, yeah. So since that got messed up, so what was the mass acceleration? And what we have is, you have great mass, and you have acceleration and you have the force acting on it. Hello, yeah. Yeah, so you can see this, all of you? Yeah. So this acceleration, basically what is acceleration? It is the rate of change of velocity. If you have velocity, a change in velocity and change of time, this is what our acceleration is, right? Roughly speaking, right? How much, what is the change in velocity and in what time it has happened, that will give you velocity. And if you want to be very technical mathematically, then you tend this t to 0, and this we write it as dr by dt, dr by dt. Or since mathematicians are lazy people, they write it as r dot. R dot means the rate of change of, yeah, so acceleration is rate of change of velocity. So this gives your acceleration. So what I have there is mass mi into ri, acceleration, is equal to the force which is acting on the ith body. So each body gets, ith body gets attracted by the first, second, third, and so on. So this is, you know Newton's law of gravity, which says m mass into I into m1 by r1 ri square, right? This is one force. This is g mi m2 with ri2 square, and this way it goes on all the way till mi m n minus 1 n by rin square, right? And this I can write it in a neater form by writing. So see, this is the only equation, so don't be scared. It just shows the power of mathematics, where you have mi ri by rj, rij square, and in the direction of rij. This is your equation of motion, and I can get rid of this mi on both the sides. That's why I have only gmj rij square. And j goes from 1 to n. J should not be equal to I, because a body does not exert force on itself, right? So when you have R1, then you cannot take one here. You take the second one, third one, fourth one, right? So this is the equation of motion, and the beauty of writing it this way is, if I make this n as 3, then it's for the 3-body problem. When I write this as 2, it is for the 2-body problem, and when I write it as 1 million here, it is for the million problem, right? So this is a very neat way of writing it, and mathematics, as we know, is basically a set of notations well used and powerfully used. So left hand side was ri double dot, which has got jumbled up there. Okay. So like it was told by your friend, if you have only 2 bodies, then you get only 2 equations of motion. First one giving the motion of the first body, and the second giving the motion of the second body, and you have to solve it. And when you solve this equation, the solution which you get is of that kind, r equal to p1 plus e cos theta minus phi. So what that indicates is, by changing e, I get different things. When e is 0, you get a circular orbit. So you have one body and the other one going around, it becomes the other is going around it in a circular orbit. When I take e lying between 0 and 1, it becomes an ellipse, right? It's a flattened circle. And when e is equal to 1, it becomes a parabola. And when e is greater than 1, it becomes a hyperbola. So the only possible solutions you get are these conic sections. And strangely, 2000 years before the solutions of this problem were brought, people were interested in sections of a cone. They are called conic section because if you take a cone, a dunce cap, and you take cross sections, if you cut it perpendicular to the axis of symmetry, you get a circle, right? If you cut it at an angle, you get an ellipse. You shift your Cutting angle a little more, you get a parabola and then a hyperbola. So these Egyptians were studying conic sections 2000 years before solutions of the n-body problem were being discussed, and they had worked a lot on these things. And many a times it has happened that mathematics was developed, it was of interest to people for some certain reason, and later it became essential for the progress of science, right? Another similar case is of differential geometry. Differential geometry was studied by mathematicians, and when Einstein had to give his general theory of relativity, he needed a language, and that was differential geometry, without which he could not have given his theories. So mathematics many a times was developed before it was applied to physical problems. It was being studied for the beauty of the whole thing, and later it became very essential. And it's such a strange thing that the only possible things you have, if you have a two-body system, the only possible solutions are a circle, an ellipse, a parabola, or a hyperbola, right? In school, you must have done problems where a projectile, you throw a rock and it takes a parabolic path, right? That's what it is. And the Earth is going around the Sun in elliptical orbits and so on. So these are the thing. And how does E, you get different values of E? It changes when your initial conditions change. So it depends on how far each of them are. What is their relative velocity? So as you keep changing the velocity, you get different things. You get either parabola, hyperbola, and so on. Okay, so yeah, so this is the elliptical orbit, and this is, yeah, let's not get into this. And here we have various possible motions of a two-body problem. They are going in ellipses, but this is one of the ways they can. You can have, oh, again, that GIF is not moving. And they are all muddled up. I should have connected my laptop, I think. Yeah, so all these equations are messed up here. I don't know why. Let's see if I can go on. Yeah. You can follow me, right? Yeah. Okay, so coming to the three-body problem, two-body problem we could solve, right? And we have seen some orbits. By changing initial conditions, you can get all kinds of different orbits. And when you have three bodies rather than two, then the whole thing becomes very complicated. And it was shown by Poincaré in 1857 that there are no general solutions for the three-body problem. It's impossible to find a general closed-form solution. But interestingly, he showed that there are infinitely many possible periodic solutions and infinitely many non-periodic solutions. And this tells us that if you treat, say, Earth, Moon system, and you put a satellite, this is a three-body system, and you can find infinitely many orbits where you can have satellites which can go around in very periodic stable orbits, and the class is innumerable. That's why we have so many possible satellites. It's not that we have only one satellite which goes, but they are innumerable. Each country has been launching satellites, and there are thousands of them there, and they all are in stable orbits without impacting each other, because there is a possibility of that, and that's what was shown mathematically that you can create. Okay. And then interestingly, binary stars are very stable. Three-body systems are very unstable very often, and for that reason we have a lot of stars in the sky which form double stars, binary systems. Or there are galaxies, two galaxies which are going around, right? So you can extend it at different levels, and you see that the three-body system is, they do have a solution, but they are usually unstable. And here are some three-body orbits which are stable. Like you have these three which are going around in this pattern, and they would always go around without colliding each other. So the way you can handle these three body problems is by using numerical solutions, particular solutions, or using computers to solve them. Right, so so there are all kinds of different possible orbits which make it very simple and this thing. And these triple body encounters also are very sensitive to initial conditions. If you have a binary system and a third system goes past, at what speed it is going, at what distance it is going, all that make a difference, which can either lead to the disruption of the whole system, right? Or it can make it a bound system. It could make an exchange where the perturber comes, grabs one of it, and the main one gets chucked out. And right, so there are all these possible things, and by tweaking, by changing the initial conditions, by varying the distances, by varying the velocities, relative velocities, you can go from one system to another. And these are very essential for us for various things. Because we use these things to even catapult. When you are sending a probe to Mars, then you use slingshot effect by taking a close path towards the moon, and it gets gravitationally slingshotted and thrown away, right? So these two-body, three-body systems play a very important role in how the whole system evolves. So here are some more orbits, and you can write simple programs on computer, and by varying the initial conditions, you can create all these beautiful patterns, and these are all very stable orbits. This is for a Earth, Moon, and a satellite system, and you can design orbits in specific way you want the satellites to move, whether you are using it to scan the surface of Earth, or whether you are to what is the purpose of that? Whether you want the satellite to remain stationary to Earth at a specific point so that you can always be in contact with it and so on. And it is basically doing these three-body systems in a good way. This is another very interesting problem which is called the Burroughs problem, or it's called the Pythagorean triple problem. You have a Pythagorean triangle of side 4:3:5, right? The Pythagorean triangle. And you put three masses. The side, the vertex opposite to the big side, you put a mass of 5 times larger. To the side whose length is 4 times large, you put a mass which is 4 times larger, and on the third one you have a mass 3, and you let them go. And this could not be solved analytically for a long time, and only with the advent of computers people could solve it. And this is what happens. Yeah, so this was first proposed by Miesel in 1893, and Burrow revisited it 20 years later. And much later, in the 20th century, people could solve this using computers. And what they saw is finally the two large masses make a binary, and the third mass gets ejected out, right? So this is a small program which you can write and solve these problems. Okay, so these are the results, which shows that finally the least massive one gets ejected out. So extending it from a three-body system to an n-body problem, we have many more applications to that. So like we realize that solar system is not just Earth, Moon, and Sun, but you have many more planets. So technically, it's a many-body problem. And some of the ways they tried to solve the Earth-Moon system was where you took Earth, Moon as a two-body system, and the gravitational force from the Sun was taken as the perturbation. So you change the force function on the right side by a small amount, the perturbations which come from the sun, and you see how does the solution of a two system change by varying the perturbations, right? So this led to an area called the perturbation theory, which is something very essential, which can be used in life sciences, it can be used in economics, it can be used in any places, where what you do is you have suppose you have a market and you introduce certain perturbations in it, small changes in, say, the petrol rate, or you should make small changes in the labor rate and see how does the system change, whether your output becomes very different from what it initially was or not, right? So this perturbation theory, many areas of mathematics which got formalized when we are trying to study the solar system dynamics or the three body problem, they have deep impact on different areas of human endeavor. So before I go on to the extension of this three body to n body problem, I would like to touch upon the Earth, Sun and Moon system, and I would like to talk about the issue which we always face about sighting of the crescent moon. Right, this is a question. Before we celebrate our Eid, we look at the crescent moon and we decide whether it's the next month is starting the next day or not, right? So we want to see it by our naked eye and decide. Yeah. Uh, if it comes to calculation, I can tell 100 years from now at what date and what time moon will be at what position, whether it can be seen, right? But can you see it from your naked eye? It's a very tricky job. Why is it tricky? One thing we have seen that even when you look at the three body system where you take them as point masses, it is complicated. You can't find a general solution. Here we have Earth, Moon and Sun system, and the thing makes it more complicated because you have Earth moving around the Sun in a plane which is called the ecliptic, right? And Earth always remains in the same plane, 5 degrees to the plane of motion of Earth. Earth's orbit around the Sun is an ellipse. Moon's orbit around the Earth is an ellipse. And in an elliptical motion, when you are close, you have the gravitating body at the focus. And when you are close to the focus, the body goes faster. And when you go far, it becomes slower. Right? So all these planets, or even the moon which is going around the Earth, it speeds up when it's close to the Sun and slows down, and speeds up and slows down. So the velocity with which Earth is going around the Sun keeps varying, and so does Earth's motion around the Earth. And due to Sun's perturbations, disturbances, Moon's eccentricity keeps changing. It changes by small amounts. It keeps fluctuating, right? So, and then when can you see the moon? See, when the Sun, Moon and Earth come in a line, it is called conjunction. That's the day you cannot see the moon because it is in the direction of the Sun. Sun is too bright, and you see the moon is there during the day, and you can't see it because of the glare of the Sun. It is there during the day, right? When it is on the other side, moon is on one side, Earth at the center and Sun on the other side, it's a full moon. You can see it. Yeah, the Sun sets and the moon rises, you can see it. So at the time when moon comes between Sun and Earth, that's the time of Amavas, which you can calculate it very accurately to the very minute, to a very second, on which day will it be there. So this can happen at 6 in the morning, it can happen 11 in the day, it can happen at 4 in the evening, right? So if the conjunction is happening at say 4 o'clock in the evening and the Sun is going to set by 6:30, you will not be able to see the moon because there's too much of, right? So you have to see the age of the moon after the sun sets. So it should be more than a certain time, right? Secondly, setting of sun, rising of moon, they keep shifting because we are in elliptical orbits and Earth's axis is tilted and so on. So sometimes sun and moon they set together, sometimes they set differently, right? Setting of sun and setting of moon time can vary. When the sun has set, you have to see how high is the moon. So if it is more than 17 degrees, then you can probably see it, right? So these are the things which make the whole thing very complicated. It's nothing to laugh about when ulamas are unable to say whether they have seen it or not, because on certain days it's very tricky to see it. You know that the moon is there, but if you are not, if you are ready to use a telescope and use filters, then you can exactly see it. But as long as we don't want to do that, we want to rely on naked eye. On certain times, when the age of the moon is not sufficient, when the setting time and the setting of moon are too different, the duration is not long enough, then you will not be able to see it, even if though it is there, right? So it's a complicated problem, and other than that, there are issues of visibility of the atmosphere, right? So, but this data over the, yes, please. Yes, so you need 23 hours or so, yeah. And you, the sunset and should be more than 17 degrees, right? And then sometimes, 17 degrees, it's a very, actually there are many criteria. This problem has been studied by Babylonians. They had 12 different criteria to predict seeing visibility of the crescent moon. And from that, four are very important. So there are 12 because you can't very strictly say more than 17, because if they are exactly aligned like that, it's not sufficient. If they are slightly off, even 15 degrees will be enough, right? So four are very important: age of the moon, sunset and moonset lag, and the height of the moon above the horizon, and the latitude of the place. Your latitude also matters. You may be able to see it in Kerala, but you may not see it in Kashmir. That is quite possible, right? So you get a visibility a curve like that, which looks kind of a parabola, right? So same point on the lower latitudes can be seen, but higher up you will see it the next day. So most of the time, with little bit of calculation, you can exactly say on certain days you'll surely see it on this day, but on certain days it's very, very dicey. You can say the probability of seeing is very low, right? But we can calculate and sure. How many moon sightings? New moons. The whole world within 2 days. Yeah. If US sees very often in the West, there's a larger chance of them seeing it and we seeing it the next day, right? Because from the time of conjunction and setting of the sun, it is more time would have flown for people in the West, isn't it? When the conjunction is at a certain time, and for Japan or India, we are in the east, so the sunset and the moon set lag will be lower, while it will take another few hours for US for sunset, and right. So in the west they may see it on some day, and next day surely we'll see it. And it is possible that Saudi will see before India would see. On certain days it can happen. On certain days, surely Saudi and India will see it. If India has seen it, it has to be seen in Saudi and US and Europe and everywhere. But the other way around, if they have seen it in Europe, we may not see it that day. We'll surely see it the next day. It can't go beyond a day. Yeah. So, we use computers. So when we have said that two-body problem, you can actually write the equation and solve it. But for three-body, you cannot find a general solution. You have very different, very beautiful, very innovative ways of handling and solving it. And one of the methods is to use computers to write a program which will solve these differential equations and do it. And that was done to solve the Bohr's problem, and you saw the animation. And what is done is you take a time step, you take a small delta t, and you have a velocity, and this is your initial position. Your change delta t v gives you the increment of location, right? So your next position, your xi1 is xi plus delta t vi, right? So this should be in x, y, and z, all the three coordinates. And then you update velocity. Velocity is this delta t by m is acceleration, right? From the equations which you saw. So this gives you the increment in velocity. Yeah, 1 by m fi is the acceleration. Delta t is in delta t time. So what is the change in velocity? So you keep updating position and you run simulations. And to do simulations, it's very creative. Programs which are deal with it, how you can write these programs. Beauty in city, and right, and there are other ways of doing it where people have come up with special computers to solve these n-body problems. This is the picture of Arset. He's the grandfather of n-body simulations. He was the first man who started distributing his code freely to people to use it and reuse it. So you can download his code, tweak it, change it to your liking, and run simulations of your kind. And you can study how these n-body systems are all around us. Stars, when they are born in groups, right? You are born in clusters. And how do these clusters change in time? They'll take millions of years to do that, but we can run the whole thing in a shorter time on computers and see how these clusters would be after 1,000 years or a million years and so on. So here's a mosaic of galaxies. Galaxies are huge collections of stars, gas and dust, where you have billions of stars in each galaxy. Milky Way, in which we live, has about 200 billion stars, and our galaxy looks like a pancake. It has a flat disk, it has a bulge at the center and a big halo. And how would it change in time? If in 100 years, if suppose we lived for too long, 100, you will not see any difference at all. It takes millions of years for the transformation to take place. And what we observe are these galaxies come in a variety of shapes. Some look like circles, some look like ellipsoids, some look like they have spiral arms, and some have very strange irregular shapes, and people wondered why they are different. For example, you have these elliptical galaxies E0, E1, E2 to E7, where E0 is a spherical, circular looking galaxy, E1 is slightly flattened, E2 and E7 is most flattened. Then you have the lenticular galaxies where you have the central bulge and a small disk. And then you have these beautiful spiral galaxies which have large spiral arms. And right, so you have spirals with bars, you have non-barred spirals. This is the famous Hubble tuning fork diagram. And people used to think that galaxies are born circular and because of rotation they start getting flattened out and they become ellipticals. And if the rotations are faster, then a disk appears, and then in this disk for some reason the spiral arms are developed. So people thought that this is the evolutionary scheme. They are born as spherical ones because matter falls on gravitationally, and because of rotation they flatten out and a disk appears, and then the spiral arms grow out of it. And then there were these irregular and peculiar galaxies which people didn't know what they were, and people thought that there were galaxies which were not formed completely because there was insufficient star material there. But the n-body simulations, yeah, the use of mathematics could show what exactly was going on. And there were two brothers, Toomre and Toomre, in 1972. They did n-body simulations where they showed that spiral galaxies can merge to form ellipticals. This was something opposite to what people thought, right? People thought spirals are created from elliptical. Ellipticals are born first, and then you have the spirals. But here they showed that the spiral galaxies can merge to form elliptical galaxies. And here's a simulation which shows that there are two spiral galaxies which are coming, and they are see, this is the stage where we are seeing it now. So this is called the mice. There's a astronomical name to this too, NGC 2464 and 2465, but they are also called the mice. It looks like two mice which are hitting head on. And what we are seeing is these are two basically galaxies which are coming and colliding. And if I run the simulation further, you will see that in future these two will merge to form one big elliptical galaxy, right? So this will take a few million years for the whole thing to complete, but with the power of mathematics and the power of computation, you can run it within 5 minutes and show what will happen. And this is what is going to happen to these two galaxies, right? And what you see is that they are going to merge to become one big spiral, one big elliptical galaxy, right? So, so to do these simulations, you have to basically know a little bit of mathematics. Equations are right there, and you just have to solve those equations numerically, right? But while doing it, you have to take into account how gas reacts. So there's fluid dynamics in it, right? Mathematics is a branch of maths which deals with fluid, air, water, how fluid responds to disturbances, gravitational effect, and so on. So these are made up of central bulge, a disk, and a big halo. The halo, you will see it as a red thing, and they would merge. And what we are seeing here, what you see basically is these, why are these tails being created, right? It is essentially you have conservation of energy. As the potential energy of these two are getting reduced, this is being transferred to the stars in the galaxy, and they are being thrown out in these big tidal tails, right? So they are thrown out, and it's like when you throw a ball up, after some time it falls back. This is what is happening. These stars are gaining energy, and they're being thrown out to form these large, beautiful tails, these bridges. These are called the bridges between galaxies, and finally you will see that they are coming back, they are falling back to form one big elliptical galaxy. And when this happens, there are other things which changes in a galaxy, not just the morphology, not just the shape of it, but the star formation rates goes up because the gas gets compressed and there is a sudden burst of star formation which goes on. And there are many things which people could not understand earlier, why galaxies look different and how they evolve and why do some galaxies show more of star formation than others? They could be answered by using these simple Newton's laws of gravity and equations and a little bit of computing power of computers. So with this we'll come to the last slide, where not last but one. Our Milky Way, see, we know that Earth is one of the 8 planets which go around the Sun, and our Sun belongs to a collection of 200 to 400 billion stars which constitute our Milky Way Galaxy. And our Milky Way Galaxy is one such spiral galaxy. And these galaxies are they cluster up to form a local group of galaxies. There are about 54 such galaxies, each galaxy having billions of stars, 100 billion stars. So there are 54 such galaxies, which is called the local group. And in this local group, there are 2 major galaxies. One is the Andromeda Galaxy and one is the Milky Way. Andromeda Galaxy is larger than our Milky Way, about twice the size. That's also a spiral galaxy, which is shown on the right. And they are on a collision path. They are 2.2 million light years across. A light year is the distance traveled by light in 1 year. Yeah, light travels at 300,000 kilometers per second. So if it travels for 2.2 million years, that's the distance. So a light year is 300,000 into 365 into 24 into 60 into 60 seconds. Right? So it's a big number, 10 to the power of 13 meters or so. And so it is 2.2 million light years away. Light traveling at the speed of 300,000 kilometers per second will take 2.2 million years to reach us. And they are approaching each other at the rate of 500,000 kilometers per hour. The collision is expected after 3 billion years. And they will merge to form one big elliptical galaxy. And our sun's age is 4.5 billion years now, and it is going to live for another 4.5 billion years. 4.5 billion. This is going to happen after 3 billion years. So it's before our sun blows up. This collision is going to happen. And if some humans survive, they will see this cosmic drama. And this is another simulation where these 2 galaxies are coming, and as they come close, they comb into each other, distorting each other and merging, leading to star formation, other enhanced activity, and they will finally merge to become one big elliptical galaxy. Right? So this is what it will look like. And if you calculate and see, the chance of stars hitting stars is very low. So the chance that our sun will collide with another star is very low. We can calculate, and it works out to 10 to the power of minus 15. That is 0.000015 zeros 1. So the chances that our sun will survive, our sun either will get thrown on the outer edges of this combined galaxy. If that happens, then our skies will become very dark, and it will be a good time to study extragalactic astronomy. And if we are thrown at the center, then we will see many, many more stars in our skies. And this will happen before our sun extinguishes. So, so this finally, the whole process takes about 1 billion years for the 2 systems to finally settle into one big galaxy. And that's the beauty of mathematics. And I study, one of my areas which I study is galaxy interactions, where we study how galaxies collide and what will happen when there is more gas in it or less in it, right? So mathematics is not just adding numbers, multiplying and dividing numbers. Mathematics is something much beyond it. It takes you and tells you, this is very it's very essential to our survival. It helps us how understand works. It trains us to think logically and rationally. And it relates to all human endeavors. Mathematics, if you are good at mathematics, you have a place anywhere. You can do economics, you can do chemistry, you can do, I strongly believe that if you know mathematics well, you can do anything else. And most of all, it's beautiful. Yeah, so that's why we should study mathematics. So thank you.
बताते हैं
अच्छा नहीं बस हो गया
ये वीडियो
हो गया
Thank you very much, sir, for addressing us. Sir, we have a small interactive session. So, boys, if you have any questions or doubts, you can clarify it with sir.
If there are any questions, please do ask. And you can't do science, maths without asking questions. And no question is a silly or stupid question. You have to ask questions. Unfortunately, I can't see you all.
Excuse me, sir.
Yeah.
Good evening, sir. Myself Abdul Mukhid from 11th standard. My question is, means it can be logical to you, sir, or else anybody, but I'm confused in it. That sometimes we can able to see moon in daytime also, sir. But the thing is, the sun is there, sir, and there is Earth. Moon is revolving around the Earth. When Earth rotates towards the moon, there will be night, no, sir?
No. When Earth turns away from the sun, it becomes night.
Yes.
Yeah.
But at night we can see the moon,
Right.
which is towards the sides, which is away from the sun. But how can it possible, sir?
Yeah. So the reason is that Earth is moving around the sun in one plane, and Moon's orbit is 5 degrees to it. If Moon was also going in the same plane, then you are right. If the Moon was on the other side, it probably would have been in the shadow of the Earth, and you would not have seen. Right? So we are seeing the Moon because you have sun's light falling and coming to us, isn't it? And this is happening because Moon is in some other plane. Okay. So your sunlight is coming, it's striking it, and you see it. Right? That's why we don't, though it, we don't have eclipses every month. Otherwise, we should have one lunar eclipse and one solar eclipse each month, but it does not happen because the angle is tilted. So only when they get aligned and they are on the same plane, there are two times when the moon crosses this intersecting point of the two planes, node line. That's when if the sun, earth and moon system are in the same line and they are on the node lines, then you will have an eclipse. You will see the earth shadow falling and it will get hidden after some time, right? But since it is tilted away, so you have the sun and you have moon here. So that light is falling and I'm able to see it. Right? So where do we see it? If the moon is here, I see it as half the moon. When I see here, I see the whole thing. Right? And when it comes like that, then I don't see the moon at all because the sun is too bright and it is somewhere here. It should be there. Okay. And there are times when you can see moon even in the day, like you said. During the day, there are stars in the sky. but we don't see it because the sky itself has a certain brightness. As the sun rays go through our atmosphere, they get scattered, and there is a sky brightness. And if anything which is fainter than the sky brightness, you will not be able to see. Things which are brighter than that, you'll see. So moon sometimes you can see during the day because the moon is brighter than the blue sky, and hence you can see it. But
It
you
is
will not.
also closer to Earth, sir. That's why we can.
It is closer to Earth, and yeah, so the sun falls on it and it's bright enough. While stars are pretty far. If you go to the moon, you will see stars, you will see the sun there, and you will see stars around it because the moon sky is dark, right? So as the sunlight goes through our atmosphere, it gets scattered. Blue light, which has the shortest wavelength, gets scattered the most. Rayleigh scattering, which you talk, yeah. Color is nothing but the wavelength of light, isn't it? You have studied wavelength. Okay, so red light has a certain wavelength, blue light has a certain wavelength. So the shorter wavelengths have high energy and they get scattered the most. And hence blue gets scattered and hence we see the sky as blue. So if there was no atmosphere, we would have seen stars during the day too. The sky would have looked dark. Right? But now what is happening is the sky has a certain brightness. It's something like a few minutes back when the lights were not there, I couldn't see you all. Yeah, because your brightness was fainter than this brightness. So only when that is brighter than what is the background, then I can start seeing. Okay.
Thank you, sir.
Assalamu alaikum, sir.
Walaikum salam.
Sir, if the three bodies are on the same set, three bodies are on the same set, the whole world is not able to see them or some of them. Yes, as you said now, if three bodies are on the same sun, moon, and earth, we can't see the moon with our naked eye. Thank you, sir.
Assalamu alaikum, sir.
Walaikum salam.
Sir, when two galaxies was crashed, means that time what will happen?
Yeah, so this what we saw was a simulation when these big objects collide, they deform each other. There's an exchange of energy, right? Conservation of energy, and these rip each other up. They are different. How that impact happens makes a difference. If two galaxies hit each other very fast, then they just go through each other, nothing happens. Sometimes they hit each other in a slow way and ring galaxies are created, becomes a splash, right? Sometimes they go and as they are approaching, the stars from each galaxy get pushed. There's a tidal bridge formed between them, and they come close, and then they come back, collide, and they merge. So depending on what kind of a collision it is, you get different outcomes.
Sir,
So
then what happened will in Earth, sir?
what will happen to Earth? Two things are possible. Either we will go very close to some other star. Suppose our star is in this interaction goes very close, then Earth can get disturbed and get thrown away. And then that means that will be the end of life. But if we don't go very close to another star, then we may float away with the sun somewhere else, and we will continue to be in the same orbit. Right? So anything can happen. So what these simulations show is it gives you a big picture. It gives you a statistical picture, but individually what is going to happen we can't say. Probabilistic we can say. That's what I said. The chance of our sun hitting another star is very low. So the chances nothing will happen to our solar system, we will survive it. But there is a small chance that it can disturb the whole solar system and Earth will either collide with other planets or fall into the sun or get drift away. Right?
The sun and moon will be beside only. Isn't it?
Yeah,
what-
sun and moon can get thrown away together and yeah, so
Okay, sir. Thank you.
yeah.
Good evening, sir.
Good evening.
This is S.K. Ashraf. My question was, if the characteristics of galaxies their own or all are same?
Characters of galaxies are same.
All are same. Or each galaxy has their own characteristics.
They have different characteristics. There are different types of galaxies. They are different not only in their shape, but they vary also in their chemical compositions. Right? What kind of stars there are in the galaxy? Whether the stars are old stars or young stars, whether the stars have more of higher metals or they are only hydrogen stars. So characteristics are different. So galaxies are classified. That's an important question, a good question. They are classified in different ways. One is they are classified in terms of their shape, whether they are ellipse, lenticular, spirals with bars, the shape. Secondly, they are classified in types of metallicity, how much of they have more of iron, uranium content, a lot of, or they are basically made up of stars which are only hydrogen and helium, right? Then they also depends on the amount of gas in a galaxy. Certain galaxies have a lot of gas, so there will be a lot of star formation and there will be active galaxies. While some galaxies they are devoid of gas, so no stars will form there, right? So there are different types of galaxies.
So after
And even the colors which you showed, you saw there were some reddish galaxies, some bluish galaxies, and that shows the temperature of stars. The redder galaxies are galaxies where the stars are not very hot. But the blue galaxies are where there are very bright and hot stars in it.
Sir, if yes, after merging of two galaxies, what will be happen to the characteristics? Only shape will change or characteristics also change?
The whole evolution of the galaxy will change. In the sense, one is the shape changing. Other thing is it leads to consuming of gas. Very often, most stars are formed suddenly. So it becomes devoid of gas, right? So those kind of changes also come. Not just the shape, but even the content of gas in it and other things do change.
Thank you, sir.
Yeah.
Assalamu alaikum, sir.
Walaikum salam.
Sir, I have a doubt. We all know the solar system revolves around the sun, sir. But another, there is a theory that the solar system is revolving around the sun at upward direction. Upward direction, sir.
Yeah, so basically, you have the earth going around the sun, right? It's spinning, and similarly, the sun is rotating on its axis and it is going around the galactic center, right? And the motion of the sun around the galactic center, it's about 200 kilometers per second. That's the velocity which it is going around the galactic center. And along with that motion, there is another motion where the sun is now on the lower side of our disk, but it will go up again. So the motion of this is not just a plane, but it's a wavy kind of a motion. So our sun is now with the planets below the galactic plane, but it will, after some time, it will go up, right? So in that sense, it's moving like this. So the whole system is, yeah, you are right. It's moving up like that because there's this kind of a
It's like
motion.
moving like a wave, sir.
Yeah, it's like a wave.
Okay, thank you. Jazakallah, sir.
Yeah.
Assalamu alaikum, sir.
Yeah.
Sir, is three body system stable?
Three body systems, like I said, mostly they are unstable, mostly. But under certain very strict conditions, they can be stable. But mostly they are unstable.
Sir, as you said that they are unstable, so if we place a satellite between Earth and Moon system, we see it moves in perfect elliptical path. So as you said that they are unstable.
Yeah. So these satellites have a certain time for which they are sent. You know, the life of each satellite is 4 years, 10 years. After that, electronics, technology, everything becomes obsolete. So then they are sent into the satellite graveyard, right? So we want to keep these satellites in those orbits for a certain period of time. And for that, they have certain thrust motors there, which they keep shooting to correct the position. So when they are drifting away from that orbit, their corrections are done, right, to keep them, to get them back again and again. So left alone, they would wander off because most of the time these three bodies systems are very unstable. So these are constantly corrected, and then after a certain time, you let go.
Okay.
Yeah.
Assalamu alaikum, sir.
Walaikum salam.
Sir, you said that geocentric theory was proposed by Ptolemy and heliocentric theory by Copernicus. At that time, how he was able to prove that Ptolemy theory was wrong?
Yeah. So technically speaking, almost 100 years before Copernicus, there was one Greek astronomer and mathematician called Aristarchus. He had also given the heliocentric theory, right? So the debate is on whether Copernicus knew about his work or not, but there were certain things which were not very conducive to geocentric system because it could not explain various things. See, why does Venus show phases? Right? Venus also changes its brightness. It's because Venus is an inner planet and it is on different points around the sun when we are looking from the earth. So sometimes Venus is on the other side of sun and you'll see it very bright, and sometimes Venus is closer this side, so you see only a part of Venus. So there were certain things which were not very good, and hence people were thinking of alternative theories. Another thing was that Ptolemy's model was very complicated because you have Earth going around the sun. So if you see from Earth's perspective, yes, sun is going around us, but Mercury is going around sun. So Earth will see it going as loops, as cycloids. Mars will be still crazy, Venus, right? So to give a simplified model, Copernicus thought of this, and Copernicus was afraid that people will laugh at him. So only when he was dying, on his deathbed, he released the book. And he gave it as an alternative theory to, he didn't believe totally that sun is at the center. People believe that Earth is huge, Sun, now we know Sun is so much bigger. Yeah, now we know Sun size is 1.5 million kilometers diameter. But at that time you see it as a small disk. So it was not realized that Sun was such a big object. So Copernicus was afraid to give his theory because he thought people will laugh that how can Earth move? That was the idea. How can Earth move? It's so big. While Sun is small, that's why it's going around. Right? So, and he only when he was dying, only then his book was released because he thought otherwise people will laugh at him. Right? So, and then other people who supported him, like Galileo, it took another 100 years for people to accept Copernicus' theory because they thought he was mad, it was not right. And even when Galileo used telescopes and he proved that Jupiter had planets which were going around it and Earth was not the most important thing, there are other objects which also has bodies going around it. He was troubled a lot by the church. Right, so it went to a tremulous period where many mathematicians, astronomers were treated as heretics because people thought that they were going against the Bible, the religious scriptures, and it required a lot of courage to give these theories. Right, they were troubled a lot, and some people were even burnt at stake. They were killed because people thought that what they were saying doesn't agree with what the scriptures were saying.
Thank you, sir.
Yeah.
Sir, this Keplerian law, as you said, square of the period is directly proportional to the cube of its distance. Is applicable to all bodies, three bodies?
Yes. Yes. For any two, if you have any two-body problem, right? See, he's treating Sun and each planet individually. If you treat it, right? You can show that if I have two bodies, one central body and one going around it, I can show that T square is proportional to A cube. This will always happen. For any two-body system, it will happen.
As you said, two bodies will form binary and third body will be ejected.
Yeah, very often that's what happens. But I also showed you some special cases where they can form a triple system, right? There are some stable configurations where three bodies can survive like that forever and ever if they have the right positions, right velocities, and so on. Yeah, but like you said, for any planet, any star with any planet around it, where there's this T square will be proportional to A cube. That you can show it mathematically with your 10th, 11th class mathematics.
Thank you, sir.
Yeah. But what Kepler did was he had data, and data showed that this law holds. Yeah, there was data of observations, and he could fit a formula which showed time square is equal to the A cube distance cube. But we can now, using little bit of calculus, I can prove it that this will always hold for all planets going around the sun.
Sir,
mathematically.
As you said, it is popped up that n periods formula, r cube in denominators there. For n period. R cube, guys.
I have written r cap here, therefore I have written r square.
Yeah.
If I make this a vector, then this will become r cube. So Newton's law, you know, right? Newton says that when you have two masses m1 and m2, there is a force of gravitational attraction between them. This force is proportional to product of masses, and it was inversely proportional to the square of the distance between them. Square. And the direction of force is, when I want to put a direction, then I put an r cap here, unit vector, only for direction. And when I want to make it a vector, I have to divide it by r cube here. So when I am putting a unit vector here, then it has to be square here. Right? If I put an arrow here, you have done vectors in school? No. Vectors.
Yes, yes.
Physicists, they believe that there are two types of physical quantities, some which are scalars and some which are vectors. Scalars have only magnitude component. For example, time, right? It has only a number. But vector has a magnitude as well as direction. For example, velocity, right?
Yes.
So vectors are represented by an arrow on top, which has one component which is its magnitude, only the quantity, and the other part is the direction of it. This is a unit vector in that direction. So this is my vector, and one unit I represented by a cap, while right. So this is giving you the length, right? And very often this is written as only a. They write it like that.
Only that.
Okay.
Yes, sir.
So basically, when I am dividing it by r cube, I have r here. If I keep a unit vector here, then I have to keep a square.
R square.
Yeah, you noticed it very correctly.
Yes.
Yeah.
Thank you.
Yeah, very good. But that's not a mistake. This is fine.
Sir, as is shown in your slides, when Earth revolves around the Sun, one time Earth will come closer to the Sun. Then season change should be, all the countries should have same season change.
Yeah. So you have Earth going around the Sun in ellipse.